So I'm not going to lie, calculating projection matrices is actually kind of a chore. If you think about the formula we need when we define the projection formula, it's x times the inverse of the gramian of x times x transpose. And inverting the gramian takes a lot of effort. So a lot of what we do sometimes is to try to sort of construct a theory that allows us to bypass that ugly calculation. And one thing I'd like to point out is that the calculation is not always difficult. The lower the dimension of the space we're projecting to is, the easier the projection is. So let's say that the space we're interested in is one-dimensional. What this means is that the space big V is the span of a single vector called V1. So the picture would look like this. We start with our single basis vector, V1, and the space we would be interested in this situation is the span of that vector, which is just all multiples of that vector. So we're starting with a line here. What does the projection formula look like? Well, we have our basis vector. It's just one vector. And so we could put that into the column of a matrix with one column, and that's just the vector itself. What happens when we apply the projection formula? We get the projection is V1 times the inverse of V1 transpose times V1 transpose. But let's remind ourselves, what is V1 transpose times V1? That's the inner product of V1 with itself. And the inner product of any vector with itself is its length squared. So we can simplify the projection formula when the space we're projecting to has dimension 1. And what this ends up becoming is 1 divided by the length squared of the basis vector multiplied by the basis vector as a column multiplied by the transpose of the basis vector, which would be a row. This is not terribly difficult to calculate because we don't have to invert a matrix here. We're just dividing by a number. Let's see an example. So let's say V is spanned by this single vector 2, -1, 2, -1. How do I calculate the projection in this case? Well, here my V1 is this vector. And so projection is given by this matrix. Where did I get this matrix? Well, I'm taking 1 divided by 10. And the thing to notice here is that 10 is the length squared of this vector. 2 squared, which is 4, plus -1 squared, which is 1, so that's 5, plus 2 squared, which is 4, so that's 9, plus -1 squared, which is 1, that's 10. So we're taking 1 and we're dividing by the length of my basis vector squared, which is 10. And then what about this 4x4 matrix here? That's V1 as a column multiplied by V1 as a row. So that's 2, -1, 2, -1 as a column multiplied by 2, -1, 2, -1 as a row. This 4x1 multiplied by this 1x4 gives me a 4x4 matrix. And that's the second ingredient in the projection formula when the dimension of the space is equal to 1. So in general, if you give me a space and ask me to find the projection matrix, I might find that kind of annoying. But if I know the space has dimension 1, I just have to do this, and I don't find the task particularly difficult. So that's the lesson here. Projecting when dimension is 1 is not so bad. And so now I want you to think about the general situation. If the dimension of our space is D, let's look at the projection formula. It's x times the inverse of the gramian of x times x transpose, where the columns of x form a basis of the space. The difficult part of this problem is inverting the gramian of x, which for a d-dimensional space is a d by d matrix. So that's a tough problem. As D grows, if the space is very large, it has large dimension, calculating this projection matrix is not so easy. So when the dimension is large, the problem of projecting is difficult and frankly kind of annoying. So here's a useful idea. Remember, if we find the orthogonal complement of our space, the rank nullity theorem tells us that the dimension of our space plus the dimension of the orthogonal complement equals the dimension of the ambient space, n. So if the dimension of V is really large, that means the orthogonal complement has dimension that's really small. So large spaces have small orthogonal complements. And remarkably, this turns out to be quite useful, because we have a theorem that tells us that if we take the projection matrix onto a space V and add that to the projection matrix onto the orthogonal complement of that space, V perp, the sum of those two projection matrices is always equal to the identity matrix. And this is huge for us, because what this means is that if we want to find the projection matrix onto V, but V has really large dimension, we could instead find projection onto the orthogonal complement and then solve for the projection onto V using this formula. So the punchline here is that if we want to project onto V, we could use this formula. Projection onto V is the same thing as identity minus projection onto the orthogonal complement times V, which ends up being the vector minus the projection onto the orthogonal complement. So when our space is really big, and by big I mean has large dimension, it's actually easier to project onto the orthogonal complement. Let's see an example here. Here, I'm looking at the vector 4, 5, 14, 1, and my goal here is to project this vector onto the space V, which has a basis given by these three vectors. This problem's kind of annoying, because what we're writing here is some space that has dimension 3. And a dimension 3 projection problem requires me to invert a 3 by 3 gramian, which I don't want to do. So instead, what I can do here is I can look at the orthogonal complement of my space. The orthogonal complement V perp here will only have dimension 1. And that single basis vector is given by 3, 1, 3, 1. And projecting onto a one-dimensional space is easy. I can apply the projection formula we developed a few slides ago. So it's easier in this problem to start by projecting onto the orthogonal complement. So the V1 I'll use in the projection formula is my single basis vector for the orthogonal complement here, 3, 1, 3, 1. And my projection matrix ends up being 1 over 20. So that's the length of 3, 1, 3, 1 squared, multiplied by this 4 by 4 matrix. So again, 20 is the length of V1 squared. And this 4 by 4 matrix here is V1 multiplied by the transpose of V1. And then now I'm going to multiply by the vector V that I care about, 4, 5, 14, 1. And when I do this product, I end up with the vector 9, 3, 9, 3. That is the projection of this vector onto the orthogonal complement of the space that I care about. Now, of course, here, this isn't the projection that I originally wanted, but I can figure out the projection I really wanted with subtraction. I now know if I take the V I started with, 4, 5, 14, 1, and subtract off its projection onto the orthogonal complement, 9, 3, 9, 3, numerically here, I'll get the vector negative 5, 2, 5, negative 2. And my theory tells me that that is exactly the projection of the vector I started with onto the space that I cared about. And so here what I've done is I've bypassed a difficult three-dimensional problem by only solving an easier one-dimensional problem. So I've made my life easier by reducing the dimension in this example. So I think that's pretty cool.